So I'm going to talk about using trigonometry to find resultant vectors and to resolve vectors and then combine those two. So I think this is something that people find tricky at the start of A-level physics when you're starting mechanics, and it's something that comes up all the time and continues to come up throughout both years of the course. So I thought I'd start with resultant vectors. So if you're adding vectors together, now you're going to need to be able to add together vectors which are at right angles to one another. So if we have two vectors at right angles to one another, let's put them like that and give them a size. Let's say 6, let's go with newtons, let's go with 8 newtons. So if they're tail to tail, then you're going to complete the parallelogram like this to find the size and direction of the arrow or the resultant vector. So that's going to look like that. So when I combine those two vectors, the 6 and 8 Newton vectors, we end up with an arrow that looks like that. So we're going to have the size of my resultant vector, let's call it r. We can use Pythagoras, so that r is the square root of 6 squared plus 8 squared. So let's go with root 36 plus 64. Those are in brackets. Probably best to make sure that we do that before we do the square root. And then when we add those together, we get root 100. So that is 10 newtons. So the size of our resultant vector, we've used Pythagoras to do, and we've got 10 newtons. If we want to find the direction, we need to be able to describe that vector in a way which tells us the direction relative to something that we know. So the easiest way is to do it relative to one of the vectors. So we're going to find the angle theta, and the angle theta is going to be anti-clockwise from the 8 Newton force. We could find a different theta, but we won't. We could go that theta prime, which would be clockwise from the 6 Newton force. You could say things like from the horizontal or from the vertical. It depends on how the problem's set up. So to do this, I can think of my parallelogram as a right angled triangle, with this being my opposite side, this being my adjacent side, and this being my hypotenuse. So the opposite side's opposite the angle. The hypotenuse is the longest side, and the adjacent side is the side which touches the angle. So we're going to use SOHCAHTOA. So SOHCAHTOA, some people draw it out with like SOHCAHTOA, and that's kind of shorthand for the S, the C and the T are sine of the angle, cosine of the angle, and the tangent, I don't want the G, of the angle. And that equals, just going to use the first letters, the opposite over the hypotenuse side, the adjacent over the hypotenuse side, and then the opposite over the adjacent side. So in this case, we know the adjacent side and the opposite side. So we've got that one and that one. So it makes sense for us to use tan. So for us, tan theta equals opposite, which is 6, over the adjacent, which is 8. And if I want to move tan to the other side to get theta on its own, when we move things to the other side, we have to do the inverse. So in order to get theta on its own, the inverse of tan is tan minus 1 on your calculator, and that's going to be of 6 over 8. Let me just grab my calculator, didn't think that through. So I'll do the 6 over 8 in a bracket. To find tan minus 1, you can use shift tan usually, and then 6 divided by 8 in a bracket, and that's equals. So when using trig functions, sometimes you're told that you can use 3 significant figures. In this case, let's go with 3, because if we go with 1, it's getting up as 40, and that's not great. And that's in degrees. The other thing that we need to make sure is that our calculator is in degrees mode, not radians. We'll do radians in the second year, but we do all of our angles in the first year. No, that's not true. We'll use radians potentially when we do waves as well. So you need to be able to switch between degrees and radians. Maybe that's a video for another day. So in order to describe my resultant vector here, where I've got 2 vectors which are at right angles to each other, I'm going to say my resultant force R is 10 newtons anti-clockwise, 10 newtons, 36.9 degrees anti-clockwise from the 8 Newton force in this case. Alright, so we're just working with vectors and trigonometry today, so we're not going to worry about vectors which aren't at right angles to each other. Maybe we will right at the end. Maybe we will do a little bit of that, but we're going to have to do it using trigonometry, because that's a different video for scale drawing and things like that. So let's think about what is almost the opposite of resultant vectors. Let's move that up to the top. Resolving vectors. So when I say this is the opposite, what I mean is we're going to take a vector. This is quite good because I can tell what the angle is. So then I've got my vector like that, and that tells me that that's actually 0 there. I'm actually going to make this much longer. I'll explain why, because I don't want that line to be part of what we do. And then we know that that angle there is at 30 degrees. So let's say this is the ground. There's a little flower. And there's some grass and stuff. So this is the ground. This is a vector. It's easiest because you're going to use it for projectiles. So that's a vector v for velocity. And then let's say v equals 3 meters per second. So we've got 30 degrees and 3 meters per second. So what I do in these situations, I think of the whole world as being in a big Cartesian coordinate system. That definitely does not look like 90 degrees to me. It tells me it is. So this is my y direction, and this is my x direction. So it's like the whole world in this two-dimensional plane is one giant graph. And what I want to find is how much of my vector v is in the x direction and how much is in the y direction. Now, you don't have to use x and y if it's not useful. We'll look at a situation in a minute where it wouldn't be useful to use x and y. We want to split our vectors when we resolve them into 2 perpendicular components. So 2 components which are at right angles to one another. I wonder what would be a good, and let's go red. So I've got a vector there, which is going to represent my x component. I've got a whiny dog, I do apologise. Let's get my ruler back. And let's have this one up like that. So then I've got my vector v split into a horizontal part and a vertical part. Now, using trigonometry again, we can see that this would be our opposite side, this would be our adjacent side, and this would be our hypotenuse. So what I want to do is I want to find the magnitude of the opposite side, and I want to find the magnitude of the adjacent side, knowing the hypotenuse and knowing an angle. So I'm going to label this Vy, so that's V in the y direction. I'm going to label this vector here Vx. So I know to find anything to do with the opposite side, when I know the hypotenuse, I can use sine theta equals opposite over hypotenuse. Now in this case, I know the hypotenuse and I want to find the opposite. So I'm going to multiply both sides by h. So I get h sine theta equals O. So for us, O is Vy. So Vy equals V sine theta, which is 3 times sine 30. So Vy in this case, because sine 30 is a half, equals 1.5, and it's still in meters per second. This is really useful because we can treat the horizontal parts and the vertical parts of velocities, displacements, accelerations. We can treat them all completely separate to each other. So we can do operations on the horizontal part that don't affect the vertical part, and we can do operations on the vertical part which don't affect the horizontal part, which is cool. For my Vx, we know that cos theta is the adjacent side over the hypotenuse side. Again, multiply both sides by h, so I get h cos theta equals A. So my A is Vx this time. So Vx equals V cos theta, which is going to be 3 times cos 30. Cos 30 is probably root 3 over 2. And I don't know how to do that off the top of my head. So Vx equals 3 times root 3 over 2, I think, which is 2.6. Could be wrong. Correct me in the comments if I am wrong. So that is a way to split a vector into 2 perpendicular components. Then if you're doing SUVAT, you can know things about the vertical and know things about the horizontal. You can treat them completely separately, and then you can use time to join them up if you want to use something that you know. So if you know something about the vertical, like how far it fell and the acceleration for something in free fall, then you can find out how long it took to fall. And then if you knew a horizontal velocity, then you can know how far it travelled in that time, which would give you the horizontal distance, which is also known as range. So I said it wasn't always the case that splitting them into x and y would be the best. So in a case where I have, I don't want 1 degree, I want 0, there you go. In a case where I have something on a slope, and I have a centre of mass, and then I have a weight, mg. In this case, if I split it in my x and y directions, for this thing which is at an angle to the horizontal, then I just get mg, and I wouldn't get anything useful from mg. But what I can do is I can split mg, say this was stationary, and we had a frictional force up like that. and we had a reaction force up like that, a normal reaction force, so those two are at right angles. Then, if I can split mg into two perpendicular components, which are in the same directions as r and fr, then I can either find out the sizes of them. So now these two components of mg are useful to us, but they're not in the x and y directions. So if I know this angle here, then I know this angle here. And again, that's something for another time. You can kind of prove that if you like. You can look at that angle in there and then do some opposite angles and find this angle, which in this diagram is teeny tiny, up in there. I'm not going to be able to delete that. Yeah. You can prove that to yourself if you like. But here, to find this side, which is in the opposite direction to r, it's almost always going to be equal to the normal reaction force, because it's likely that the block isn't falling into the slope or jumping off the slope. So I can do, as I did before, so this is my adjacent side, mg cos theta, and that's going to, for a body in equilibrium, that's going to equal r. And then for this other side over here, I can do mg sine theta, and then for a body in equilibrium, that's going to equal the friction, which is acting up the slope. But you can also do things like have mg sine theta be bigger than the friction, and then you can have a resultant force and you can find an acceleration. And we'll do that when we look at Newton's second law. We'll do lots of different cases where the forces aren't balanced, so we get an acceleration. So I did say that we might be combining resultant and resolving vectors. There we go. So if I've got two vectors, and I'm not going to use my ruler for this, I'm just going to go for it freehand. Two vectors like this. My two vectors like this aren't at right angles. That can be some angle theta if we like, but it's not that useful to us to know that at the moment. What I can do is I can resolve, if we call them, let's say A and B, then I can resolve, I can get A, Y, and then I'll get some different B, Y, and I can get A, X, and B, X. So then to find, if I call R my resultant vector again, if I do Rx, so the part of my resultant vector in the x direction would be AX plus BX, but in this case actually that's going to be negative, so it's going to be AX minus BX, and then RY would be AY plus BY. So I've resolved my two forces in this, let's call them forces, my two vectors. I've resolved my two vectors, A and B, into perpendicular components. That's the resolving part. But I've made it so that those perpendicular components are the same for A and the same for B. So now if I've got two vectors going in one dimension, I can use just plus and minus to add them up. So then I can use my resultant vectors. I'd end up with, in this case, quite a long RY, and then quite a short, because AX was bigger than BX, quite a short RX. And then I can complete my parallelogram. Whoop, do that up there, so R is like that. So then I can go back to my finding resultant vectors, and I can do R equals, so using Pythagoras to find the magnitude, let's open a bracket, Rx squared plus Ry squared. and then I can find the angle, that one, just for convenience. So I can say my angle theta is going to be the inverse tan of the opposite side, which is Ry in this case, over the adjacent side, which is Rx in this case. So using that method, I can split, if I've got 10 different forces acting on a point, I can split them all into components in the x and y directions, like we talked about before, and then I can resolve them all. I can add them all up in the x direction, add them all up in the y direction, and then use my resultant vectors to find the final vector. So the result of having all of those vectors acting at the same point. It could be that it's 0, and then you'd have an object in equilibrium if they were all forces. Hopefully that is a bit of a refresher on vectors. Thanks for listening. Drop a like and subscribe. Thanks very much.